Okay, welcome back. Here we're going to take a look at another possibility for question 1 in this year's chemistry exam, and this is the iron tablet titration. Okay, so generally there will always be some question related to the use of iron as a supplement, as a dietary supplement. And anything in that vein tends to center around basically this keyword here, anemia. Okay, so why would we take iron as a supplement? Well, if you have low levels of iron, if you're iron insufficient, then taking iron tablets to actually replace the iron in your body is generally the common treatment, okay? In that sense, we will prescribe iron tablets, and that will be in the treatment of anemia. And that's pretty much all you need to remember. The iron in the tablet is probably worth remembering that's needed for hemoglobin in red blood cells. Here you can see the iron at the center of a hemoglobin molecule. You don't need to remember this level of detail, obviously, but just these key terms here for any questions that might come up related to the use of iron supplements. Moving on to the titration itself then, here, our titration is going to be between potassium permanganate and iron 2+ ions. So this section here relates to the actual titration. Okay, so the iron in the tablets will create a solution of those, we'll crush our tablets, make up a solution, titrate it against standardized potassium permanganate. Okay, and that's pretty much the experiment. But of course, the KMnO4 itself is not a primary standard. Why? Well, KMnO4 is unstable, it decomposes over time, and it's affected by sunlight. And this is a key point to remember with the KMnO4 solution. Whenever we have a solution of KMnO4, it has to be standardized right before we use it to standardize our iron tablet solution. Okay, and that's because if you've made it up the previous day or a few days previously and you standardized it then, concentration is probably not the same a few days later because, of course, it's decomposing over time, or if it's been exposed to light, the concentration is likely to be less after a bit of time. So for that reason, it's often asked, why must it be standardized before the titration actually happens, like right before it? And that's the reason for that. Okay, our KMnO4 then will be standardized by titration against ammonium iron 2 sulfate. This is a primary standard, so it's a pure stable substance that we can create a solution of known concentration from, and we can use that to titrate against the KMnO4. So in fact, both of these steps are actually the same. Here, it's an iron Fe2+ from our ammonium iron 2 sulfate, this standard solution that we're using to standardize the KMnO4. And then once the KMnO4 is standardized, we're using that to standardize the iron tablet solution. But again, it's the same reaction in both instances. Yeah, we have KMnO4 versus Fe2+. Okay, so that's some of the key details about the KMnO4. In terms of the actual questions themselves, they tend to, there will always be some part, again, like we said in the previous question where we were talking about the iodine thiosulfate, that you would probably be asked the very steps for making up the thiosulfate solution. Here too, they would no doubt ask you a question about how your iron tablet solution was prepared. So the various steps involved, so that you would take your tablets, you would crush them in a mortar and pestle, you'd dissolve them in a beaker with a stirring rod. Very important here when you're making up your iron 2 sulfate solution that we always add H2SO4, dilute H2SO4, and this prevents the aerial oxidation of Fe2+ to Fe3+. This is a very important detail, again, always asked. And then, so that's in, at whatever point you will add that, then we transfer to volumetric flask. The usual steps, basically, washing, all the washings, wash the beaker, wash the stirring rod, wash the clock glass, all those washings transfer to the volumetric flask. And then we bring it up with a wash bottle and a dropper to the mark and invert it several times to make sure it's homogeneous. So all the usual steps for making up a standard solution, but it will tend to be asked here as well. Okay, so our KMnO4 is going to be in the burette. Note that when we have KMnO4, because it's not a transparent solution, we'll always be reading the top of the meniscus. Okay, so we'll read from the top of the meniscus to the top of the meniscus to get the titer. So that will be in the burette. Our iron solution will be in the conical flask. Now, again, in addition to having my iron in the conical flask, we will also have more dilute sulfuric acid in here as well. And in this instance, it's to ensure the full reduction of manganese from a +7 oxidation state in MnO4- to a +2 oxidation state in Mn2+. Okay, if you don't have sulfuric acid here, again, in that situation, you get manganese dioxide form. And manganese dioxide is brown with an oxidation number of +4. Okay, that could also be asked. Okay, so remember that H2SO4, dilute H2SO4 is being used in the making up of the iron 2 ion solution. but it's also used again in the conical flask. Okay, here to prevent aerial oxidation and here to ensure the full reduction of the manganese from MnO4- to Mn2+. You need to remember all these details. The endpoint will be related to the potassium permanganate. So it's going to be when we see a first permanent pink color in the conical flask. Okay, as we drop it in, the purple will disappear, change to colorless. But as we run out of Fe2+ ions in the conical flask, they can no longer reduce the permanganate. So we're going to be left with the purple of the KMnO4, which will appear a faint pink when it's diluted, of course. Okay, so the first permanent pink color that doesn't disappear, that marks the endpoint. Okay, so let's take a look at this question. So here we're told our average titer is 13.9. We have 25 centimeters cubed of our iron solution in the conical flask, and the other details are up here. So our KMnO4 is basically going to be 0.01 molar, and the titer is 13.9. So this gives us enough information to find the number of moles of KMnO4. So it's 0.000139 moles. Now, if we look at the equation, which again you'll be given in the exam, it's a 1:5 ratio. So we will have 5 times that number of moles of Fe2+ ions. Okay, so this gives us the number of moles of iron 2+ ions in the conical flask. Now, the first part of the question is to find the concentration of the iron in the original solution. Now, the point here is the concentration of the iron in the conical flask is the same as the concentration of the iron in the volumetric flask, because of course they're the same solution. We took it from there. Okay, so we can find the molarity of that using this equation. So 1,000 times the number of moles divided by the volume, 25, gives us a concentration of 0.0278 moles per liter. Okay, now we want to find the mass of iron in one tablet. Okay, remember of course that we have 4 tablets originally. So here we want to find the number of moles in 250 centimeters cubed, because of course this is the solution that we got from 4 tablets of iron. Okay, so if the number of moles, if this is the concentration, and we know we have a volume of 250 centimeters cubed, then we can get the number of moles in our volumetric flask. So it's 50 times the molarity over 1,000 gives us this number of moles. Okay, so this is the number of moles in here, in our volumetric flask. Now, that number of moles, of course, what mass would that be? Well, to get the mass, we can simply multiply by the relative atomic mass of iron, which is 56. And that gives us this mass here. Okay, 0.3892 grams. But of course, that corresponds to the mass of 4 tablets. So now we'd simply have to divide by 4 to get the mass of 1 tablet. Okay, the last part's quite simple. They'll tend to ask you to get the percentage by mass of iron in 1 tablet. Okay, so since we know how much iron is in 1 tablet, and we know the mass of 1 tablet, we were told earlier on, is 0.36 grams, we're simply putting the 0.0973, the mass of iron, divided by the total mass of the tablet, and we are multiplying by 100, of course, to get final answer of 27%. Okay, so that's the iron tablet, and they tend to be the main things that will be asked there going on any past questions. I do take a look at the past paper questions. So if we look at question 1, we can see where my iron tablet came up. So it was last seen in 2009 and 2003. So there's been a long stretch where we haven't seen the iron tablet question. So yeah, do keep an eye on it for this year. Okay, thanks for listening, and keep tuned for some more videos on these on the 3 experiments. Okay, bye.